We will now discuss simple but very powerful cryptographic primitives, which will allow us to realize all kinds of other cryptographic problems. If you want, think about it as the universal gate of quantum cryptography, just as gates in a circuit can be universal for classical or quantum computation. We call this primitive weak string erasure, and we will soon see where this name comes from. I will again draw this primitive as an idealized box that provides some functionality to Alice and Bob. What weak string erasure will do is that it will give a string x1 up to xn to Alice, and to Bob a subset I chosen at random, as well as the elements of the string x corresponding to the position in I. For example, if I is 20 and 30, then xi is simply x20 and x30. If this should be some form of cryptographic primitives, we want some conditions. The first one is just correctness. Correctness just means that what we've just described actually happens. Alice gets a string x, Bob gets a subset I, and a substring xi. As you might have guessed, there's also some security conditions. They might seem a little bit odd at first glance, but if you think back to our protocol based on BB84 states, you can see that they're quite natural. In essence, weak string erasure is a primitive designed to capture the essence of a quantum protocol and abstract it as a separate cryptographic primitive. The first condition that will demand is that Alice does not learn which bits Bob knows. In other words, she does not learn the subset I. There's also some security condition against cheating Bob. Namely, we will demand that even though Bob may of course learn roughly half the string, namely the string xi, his probability to guess the entire string, all of the bits in xa, is very small. More precisely, his guessing probability decays exponentially with the length of the string. Or, if I write this out in terms of the min entropy, it means that the min entropy is larger than gamma times n for some positive constant gamma. I want to take this opportunity of talking about just a very simple primitive for being somewhat more formal in the definition of correctness and security than we've been before. Let's start with correctness. This is actually so simple that it may seem obvious or unnecessary to do it this way, but it has certain advantages. Remember that these are the correctness conditions, and we will phrase this now in terms of an ideal state. What this means is that we will formalize epsilon correctness by saying that in the ideal scenario, at the end of the protocol, if both parties are honest, they share some state, sigma AB. Alice has A, Bob has B. Alice has a string xa, so this is the A part, and Bob has I and xi. We will now demand that these strings satisfy certain conditions. Namely, Alice's string is uniformly random, which means that if I look at the reduced state of xa, it means I trace out everything but xa, it looks like the maximally mixed state. Also, if I look at just the subset, so if I trace over everything else, it looks like the identity divided by 2 to the n. Where does the 2 to the n come from? Note that I can write down a subset in terms of a string, where the bit I is 1, if I is in the set, and 0 otherwise. Of course, we want that Bob knows xi, which means that the bit of Alice corresponding to the positions in I should be the same as the one that Bob obtained. In a real protocol, we of course typically never achieve this utopian scenario. Instead, we will be happy if the real state is close to the ideal state for some parameter epsilon. Close here means close in terms of the trace distance, and you've seen many times now why this is a very useful definition in cryptography. Why is it necessary to write it down like this? Note that previously we were not able to deal with epsilon correctness. I had given you these informal conditions, but it's unclear what it means to satisfy these conditions approximately. In a real protocol, there are often probabilities of aborting. We'll send some error correcting information, which of course only works with large probability. So this is why we will only be epsilon correct in practice. Let's formalize security. We start by formalizing security against cheating Alice. If Bob is honest, he wants that Alice does not know the subset I. And again, we'll formalize this by looking at an ideal state. In an ideal scenario, Bob has the strings I and xi. Alice has some system A, and I'm just calling it A now, because we have no idea what the system is. Possibly it constrains the string x, but maybe not. You already know how to formalize ignorance. We want that the state shared between A and B looks like this. Namely, if I look at A and the I part, the subsets, then Alice is completely uncorrelated from I. There's one small subtlety in this definition, and you may have already spotted it. Namely, you may have noticed what is this xp at the end. What this means is that the entire string x can actually be defined. It exists somewhere outside of Alice's lab. This is a technical condition that is quite important if we compose the protocol, meaning we build another protocol on top of weak string erasure. Intuitively, it means that Alice should not be able to change her mind about the bits, even the bits that Bob does not know, meaning even the bits which are not in the set xi. Quantumly, this is an important subtlety, and we will discuss this in detail in the lecture notes. What we then want, as before, is that the real state is close to the ideal state. Let's now formalize security against cheating Bob. We say that Bob has difficulty guessing x. And what this means in terms of the ideal state is very simple. Namely, we will demand that the ideal state has exactly that much min entropy. Again, in practice, there are all kinds of probabilities and errors, which we hope to be small, epsilon small. So in practice, the real state will be close to the ideal state for a parameter epsilon. Note that if the ideal state has this much min entropy, then the real state has the corresponding amount of smooth min entropy. Because remember that the smooth min entropy of x given b of a state rho is given by the maximum over states in an epsilon ball around rho, and then we can consider the min entropy of that state. So here we know that in the epsilon ball there is the state sigma. So we certainly know that the smooth mean entropy of rho is larger than the mean entropy of sigma. Maybe it's even larger, but it's at least gamma times n. So why is weak string erasure useful? Weak string erasure plus classical communication can be turned into something called string commitment. We've already seen bit commitment, where we commit a single bit, and now we can commit to an entire string at once. It is also possible to use weak string erasure plus additional resources to obtain something called oblivious transfer, which we've seen before. This is quite useful because oblivious transfer is universal for secure function evaluation, so we can do anything with this primitive. Also, and this is something that we will talk about in week 10, the security of weak string erasure and that plus classical communication is also very useful to understand the security of something quite different, namely the security of position-based cryptography. Let's now have a look at a simple protocol for weak string erasure. We start with Alice and Bob, and the first thing that they're going to do is, as you may have guessed, distribute BPA-84 states, just like in QKD. Let's recap what this means. Alice chooses a random string x, 1 up to xn. She also chooses a basis string theta, 1 up to n, where again we will use 0 for the standard and 1 for the Hadamard basis. Bob this time also chooses a random basis string. So he does in fact exactly the same as he does in QKD. This also means that if you had equipment to perform quantum key distribution, and Alice and Bob would always measure in random basis, you could even later decide to use some of the output for QKD and some for weak string erasure. So we know what happens next, namely Alice sends to Bob the bit xj encoded in the basis theta j. Bob measures the qubit in the basis theta tilde to get outcome xj tilde. Again, just as in BPA-84 QKD. Now Alice and Bob wait time delta t. This is where the storage assumption will be applied. After this, Alice will actually tell Bob which basis string she's chosen. And Bob can now compute the set of indices where he measured in the same basis as Alice. Of course, he now has a string xi, namely he throws away everything where he did not measure in the same basis. And if there's no noise on the channel, indeed he has exactly the bits of the substring corresponding to I. Remember that we always need to argue two things about the protocol: correctness and security. Correctness is very simple, and we've already alluded to it here. Namely, Bob gets a substring, which is just defined where he measured in the same basis, and he has xi. We said that Alice gets a random bit string, and this is just the bit string x that she generates herself at the beginning. So the protocol seems to be correct. The question is now, is the protocol also secure? Let's first again examine security against a cheating Alice. Remember that what we have to show is that Alice cannot figure out I. She cannot figure out which bits are known to Bob. If we look at the protocol, let's see whether there's any chance for Alice to learn something about I. I've removed Alice's steps here from the protocol because her actions can be arbitrary. Bob chooses a basis, seems safe, nothing to do with Alice. Alice apparently sent something to Bob and she's going to measure some qubits, I don't know what these qubits are, to get an outcome. Alice also sends Bob a string, presumably the basis string, and Bob computes an index set. But all the time the information just goes from Alice to Bob. So all of these things happen just in Bob's lab. And of course, if there's no information going from Bob to Alice at all, not even a single bit, then it's quite intuitive that Alice cannot learn I. So the case where Alice is dishonest is actually quite simple. In the lecture notes, you can also see what happens with this funny extra definition, this funny extra string, x, that exists. In the next video, we will examine the case of dishonest Bob.